Let's have a look at the next slide, please. So just looking at a little bit more detail, we see by 2030, we see production will be roughly 50-50 from natural gas and from crude oil, although natural gas will be in the majority, and other transformations could be things like BioLPG from various routes. And we see on the consumption side, residential will maintain the majority, the large majority in terms of demand. Next slide, please. So I want to talk a little bit about the environmental aspects of LPG and other fuels, as well as BioLPG. Next slide. Now, looking at LPG in comparison to other fuels, what we find is that and when we're talking about fossil fuel LPG, its carbon footprint is relatively good compared to other fuels such as coal or oil or even wood. Now, that's in terms of its carbon footprint. Furthermore, the life cycle emissions factors, or the carbon footprint of LPG and natural gas for that matter, are at least 25% lower than that of diesel and gasoline. And next slide, please. That's not my slide. There we go. Okay, thank you. Okay, so looking at nitrous oxide and particulate matter emissions, we also see from this chart that LPG, which is the middle bar of all of the three different types of emissions we're looking at here in the first 5 columns, we're looking at nitrous oxides, and the second column we're looking at particulate matter, and the third column is also particulate matter, smaller. And we see that particulate matter, according to the World LPG Association, at least there's very little, and nitrous oxide is also there's very little emissions compared to other fuels such as coal, fuel oil, and wood, whether it be wood logs or pellets. So LPG, it burns more cleanly, emitting less nitrous oxides, carbon monoxide, substantially less CO2 and sulfur oxides and particulate matter than other chemical fuels such as coal and fuel oil, charcoal, and wood. Next slide. Thank you. So now I want to consider looking at the environmental aspects of BioLPG compared to LPG. So we know that the combustion of natural gas, it produces less CO2 than the combustion of LPG, and we're talking about fossil fuel LPG. However, methane fugitive emissions themselves are potential greenhouse gas. So when we talk about natural gas, if there are fugitive emissions, there's potential for greenhouse gases, while LPG is not a greenhouse gas. So if it leaks into the atmosphere, it quickly disperses into the air, it oxidizes under sunlight, and it's non-toxic to the ecosystem. Spills of other fuels such as crude oil or gas, they can be dangerous. Even coal, you can have coal fires, and these can cause toxic fumes and quite dangerous fires. LPG is also combustible. It can combust. And the other important point is that LPG is produced predominantly from methane processing or crude oil refining. And so this brings the discussion to the production of LPG from biomass, biogas, or agricultural waste to produce BioLPG, and the potential to be more sustainable with lower carbon footprint than producing LPG from fossil fuels. And that's the question. What is the carbon footprint compared to a fossil fuel LPG production? We'll look at the next slide and take a look at this question. So according to the World LPG Association, they compare LPG to oil and wood pellets and BioLPG in terms of damage cost. And the damage cost is euros per megawatt hour, And we see that oil has various damage costs where they put a value or a damage value on CO2, on nitrous oxide and particulate matter as pollutants. And LPG, fossil LPG, which is the second column there, shows far less damage costs compared to oil or wood pellets. And BioLPG is even less, again, because there is a smaller component of CO2 emissions. Next slide. But the question is, how much smaller? There we go. So here we see a BioLPG emissions factor of various feedstocks. So what we're talking about here is the HVO biodiesel process, which is indicative of HVO biopropane with different feedstocks and the different emissions factors or carbon footprint from those different feedstocks. So now we're looking at BioLPG, and we should compare it to fossil fuel LPG, which has a carbon footprint of 87 grams of CO2 per megajoule. Now, we look at the BioLPG footprint, we see that, yes, all of those highlighted in green there with different feedstocks, they are all relatively less than the fossil fuel comparator. However, they're certainly not what I would call a renewable or let's say a CO2-free fuel. So we have to bear in mind that at least via HVO, there is the potential still to produce carbon dioxide. And that's important, and I think this is highlighted even more in the next slide. So let's have a look at that. Okay, so this is basically taken from a work by Johnson, and he examines in detail the life cycle assessment of HVO with different feedstocks, and so he then determines the carbon footprint of these different feedstocks under various scenarios. And what we find is, depending on the type of methodology and allocation, if we talk about energy allocation, we see that, for example, we look at soy, we can see that there's 40 grams of CO2 per megajoule of emissions. So how does that compare to fossil fuels? Well, he considered fossil fuel LPG to produce 77 grams of CO2 per megajoule. However, if we look at the indirect land use changes, which is ILUC, which is the second row that I've highlighted there in green, we see that the carbon footprint actually jumps up dramatically. So when we're talking about HVO, this may be, there may be a lot of environmental externalities that we are talking about, for example, in the cultivation of your feedstocks, fertilizer, milling, the production of hydrogen, steam, and transport. And all of these things can contribute to the carbon footprint, as well as the indirect land use changes. So there we see, in fact, in that column, in that row, we see that for rapeseed and soy, we see that the carbon footprint is actually higher for BioLPG than for fossil fuel LPG. So there we need to be cautious, and the others are also very high. Palm and tallow is not relevant there. So what we should do is we need to focus on the allocation when we're talking about feedstock as a residue. And then we see in the last column, last row, which I've highlighted there, that if we talk about the feedstocks as a residue, then we see that the carbon footprint drops dramatically below that of the fossil fuel LPG. So let's then look at the next slide. So now I want to talk a little bit about biomass feedstock availability and the potential for BioLPG production for biogas gasification as well. So when we're talking about, next slide please, when we're talking about BioLPG feedstock, there are various chemical routes, different routes to produce BioLPG, and they've been talked about by various speakers before me, so I won't go into detail. We know that HVO produces predominantly the production of biodiesel, and it produces roughly 5 to 10% of BioLPG. There is another. So what we see is that BioLPG is often it's a byproduct or a co-product. There's also potential to produce BioLPG with power to X, which is an alternative method, and it uses hydrogen, renewable hydrogen, and reacts it with carbon dioxide either from the atmosphere or from a processing plant from another industry, which is probably more likely. And so that's another alternative. Next slide, please. And then, of course, there are the feedstocks for the chemical routes where we look at agricultural residues or waste. And perhaps this is more relevant to the work of Thiago, where he looked at these type of wastes from sugarcane, corn, rice, wheat, coffee, cotton, and soy. I have to thank Thiago for his assistance with this particular slide. So in Brazil, we see that there's large productions of these agricultural products, and they produce a large amounts of residues. In total, there's something around 645 million tonnes of residues annually from all of these different agricultural products. And the question is, or the research challenges are, what are the quantities of these residues which are available for chemical processing? But some of the residues may be used as fertiliser, organic fertiliser in the agricultural processes. It may not be logistical to transport these residues to a processing plant. And then, of course, what is the BioLPG yield from each tonne of these residues? Next slide, please. And then there's the other pathway which should be considered, and that's BioLPG production from biomass gasification. So what sort of potential is there for biomass gasification? Well, Silva dos Santos investigated the potential of anaerobic digestion of 7 types of organic wastes in Brazil to produce biogas. And he included some of the waste were municipal solid waste, wastewater.
Peter, could I ask you to wrap up, please?
I beg your pardon?
Could I ask you to wrap up, please, so that we could...
Yeah, this is we're almost at the last slide. So, and there were other organic wastes, including vinasse and as well as manure. So it was estimated that approximately 26 billion cubic metres of biomass could be produced per year, and the majority of this would actually come from cattle manure. And while that particular study focused on biogas to generate electricity, there is the potential to use the biomass feedstock to produce from that gasification process to produce BioLPG by synthesising the digestion gas. Next slide, please.
Thank you very much, Peter. We do.
So, can I just finish the slide? It's the last slide here.
You've already gone over because the others did finish early. So thanks very much. If you just leave that slide up there, ask Jude to come on, who will moderate the session, and maybe you can mention some of the points that you didn't get a chance to say in your discussion. So it gives me a great pleasure to introduce Jude Owudili, who is the researcher and senior lecturer at the University of Aston. And we have to thank Jude, because without Jude we wouldn't be here at all, because he successfully applied for a networking grant which allowed this to take place. So thanks very much, Jude. One thing I know for the chat, some people weren't able to participate. So Rebecca has put the Sustainable Fuels email address. So we will try to get any more questions to you. Apologies for that. Over to you, Jude.
Thank you. Keith, can you hear me? Yeah?
Yep.
Great. So yeah, like Keith mentioned, it's unfortunate we can't get most of the questions on the chat, but there's I've got some questions on my own, and there's one question for Iram, I guess. It says, is the CO2 reduction linear for your butyric acid loading? Is there a limit to this where the CO2 remain, stagnant? So Iram, that's your question.
So the reaction, the target reaction that we're actually trying to, sorry, can you hear me?
Yes.
Yeah. Okay. So the target reaction that we're aiming for is decarboxylation. So there's always going to be CO2 formed from the decarboxylation reaction, and it's possibly in a 1-to-1 ratio with the amount of propane that's produced. Does that answer the question?
I think it does. Okay, so in the absence of any more questions from the chat, I've got a question from Bruno. So Bruno, thanks for your wonderful presentation. But you want to make biopropane from glycerol, which indicates that you want to decouple glycerol production from biodiesel or green diesel. Do you see this as viable?
If I see what, Jude, I'm sorry.
Yeah, sorry. Because at the moment, the HEFA process relies on the sales of green diesel in order for BioLPG to be profitable. But you seem to want to decouple it, use glycerol as your feedstock. So how do you see that as being viable?
Actually, I'm not really want to do that. I think okay. We just brought this for the discussion as it was asked for us. I'm not working on that pathway. Actually, we in the institute we started to discuss projects regarding BioLPG a few months ago, and we are evaluating with our customer another route. And actually, when we saw this pathway from glycerin, we believe, as I said, it's a very cost challenge pathway. And so when we do those simple evaluation, we saw that we see other pathways that are more feasible at the first view, of course, than glycerin. And as we work with companies, they agree, at least the companies that came to us at least now, they agree with that view, and they choose other routes to analyze and to address.
Okay, thank you. I think my next question is to Thiago. So Thiago, thanks for your presentation. Obviously, what you mentioned to us is that the estimate made for biobutanol. You stop butyrates from becoming, can you hear me?
Sorry, it's breaking up a little bit.
Yeah, I think you're frozen. Yeah, so I was your established process, it makes biobutanol. So how do you stop butyrates from becoming biobutanol in order to get a high yield of butyrates for Iram's process?
Okay, there are some strains of Clostridia that can actually produce a fair amount of butyrate on their own, but we can also overexpress some enzymes to produce to favors the production of butyrate. And
Can you hear me?
Yes, I can hear you.
Oh, okay.
We can hear you. Yeah.
So it's very common actually to do some metabolic engineering in the Clostridia bacteria to favor the production of butyrate, to produce more butyrate than butanol.
Okay. All right. I'll come next to you, Felicity. We were all very excited with your presentation that you can make propane from inorganic feedstock, which is great. So propane yields do you get at the moment?
What propane yields? So currently, the propane yields are several orders of magnitude lower than the best quoted for various synthetic biology routes or genetically engineered routes. But I have to say that our fermentations are nutrient limited at the moment, and we need to identify required nutrients. They're also limited by scale. We're doing this at a very small scale for the analysis. We want to compare yields with those 3 other closely related species. Maybe one of them can produce more propane. And we want to understand the pathway. If we can understand more about the biochemical pathway, it'll give us insight into what required nutrients are and how things are working. So we have a fair bit of work to do yet that leads towards improving yield, but also discovering the biochemical pathway itself.
Okay, thank you. Peter, I'm not going to leave you without a question. So I just have one short question for you, Peter. From your studies, the potential for BioLPG appears to be very, very good. So could you say in the next how much LPG can be displaced by LPG?
BioLPG, that's a very good question. I think that's a kind of brings me to the slide that I didn't really have time for, and I apologise for going over time. Well, look, there are millions of tons of hundreds of millions of tons of crop residues. There's also the potential from used cooking oil and palm fatty acid, distillate, tallow, and also the large amounts of biogas from organic waste. So the real question there is, what is the cost? What are the transport issues, logistical issues in terms of getting these residues to processing plants? Can these processing plants be small and distributed, as has been talked about, or do they have to be centralised? And what are the environmental impacts as well of each of these pathways, or the environmental footprints, the carbon dioxide, carbon footprints and so forth. So I really can't answer that question directly, but I can say there is certainly opportunity for research in those areas, and there are many questions that need to be answered for each of the pathways.
Okay, thank you. I just want to thank all our speakers for this session, and this back to Keith. Thank you so much for the opportunity.
Thanks very much, Jude. We were keeping an eye on the inbox, and no other questions came in. I do apologise for those that can't use the chat. And once again, I'd just like to thank Jude for putting in that grant application, getting it funded, and then hopefully, of course, the funding was just a networking grant, which was, to allow us all to come